Good morning, ladies and gentlemen. My name is Artur Gamcha, and together with Maciej Niedźwiecki, I'm the author of the article for 65 EEE Conference on Decision and Control, describing identification of fast time-varying systems using pre-estimation and related regularization. Let me start by describing the problem that we were solving in our paper. We consider a non-stationary system that can be described by the following equation. Here, theta is a vector of time-varying parameters. Phi is a regression vector made up of past values of the known input signal. Y denotes a known output sequence, and E is a measurement noise. All of the previously mentioned variables are complex valued. A typical example of an application in which this model can be used is underwater acoustic communication in a full duplex mode. In this application, transmitter and receiver are typically in close proximity of each other and use the same bandwidth. This means that the signal received from a far-end transmitter will be contaminated by the signal from a near-end transmitter. In our case, represented by U. Of course, the signal from the near-end transmitter is prone to the multipath effect, which justifies the FIR description that we use. And the time variability of that model is caused by the motion of reflectors, which are objects in the environment, as well as the water surface. So the goal is to recover the E signal based on Y and U. And this task can be done by identification of model parameters. The figures depict typical trajectories of a simulated underwater channel. Derivation of our method is based on the assumption that inside the analysis window, parameter changes can be described as a linear combination of some known functions of time. Under this assumption, we locally describe our original system using a higher order but time-invariant model. Of course, this description is only valid inside the analysis window. Then we use the weighted least squares technique to obtain estimates of coefficients alpha, which we then use to get the estimates of original parameters for the current time instant. Then the window is shifted to the next observation, and the procedure is repeated for the next position of the window. This pointwise procedure is called the local basis function method, LBF. This approach provides high-quality estimates of model parameters, but since the number of estimated coefficients alpha can be quite high, it also requires a lot of computational effort and long analysis windows to guarantee good conditioning of the regression matrix. Both of these drawbacks can be overcome if we use a two-step technique, approximating the behavior of the LBF approach. In the first step, we obtain pre-estimates that are approximately unbiased regardless of the type and speed of parameter changes. However, unbiasedness comes at the cost of a high variance of pre-estimates. This is why they cannot be used as a final product. So, to solve this issue, we propose a post-filtration step. In these figures, we can see the comparison of LBF estimates and FLBF estimates depicted with black lines and superimposed on true parameter trajectories depicted with red lines. As you can see, FLBF estimates are almost indistinguishable from the LBF estimates, while the computational burden is much lower. So how exactly are the pre-estimates computed? It turns out that the whole expression for the pre-estimates can be approximated by inverse filtering of exponentially weighted least squares estimates of system parameters. To reduce the number of hyperparameters that can be tuned by a potential user, a statistically justified formula for the forgetting constant was also proposed. The second step of the FLBF method is Savitsky-Golay filtration. We again assume that our parameter trajectories can be locally described as linear combination of basis functions. And then we look for the coefficients alpha that minimize the cost function from the slide, where W is a non-negative bell-shaped weighting sequence. It turns out that the whole scheme boils down to low-pass filtration of pre-estimates with the filter associated with our basis. It's also straightforward to check that when parameter trajectories belong to the subspace spanned by our basis functions, then the FLBF estimates are approximately unbiased. In this work, we investigate two regularization techniques that can potentially improve the quality of estimates by achieving a better bias variance trade-off. The first one is widely known as the ridge regression. In this case, we add to the cost function the L2 penalty scaled by a regularization gain mu that we will further optimize. The second technique is based on the observation that the L1 penalty, which is known to promote the sparsity of a resulting model, can be expressed in terms of weighted L2 norm. We use this fact to propose the iterative procedure in which LBF or FLBF estimates are used to construct the weighting matrices at every time step. Then we add this new regularization term to the cost function using another regularization constant, which will be also optimized later. It turns out that, similar to ridge regression case, the reweighted estimates can be obtained by rescaling the FLBF estimates. Next, we note that we can perform next iterations of this procedure, replacing the FLBF estimates in the weighting matrix by regularized estimates from the previous step. This results in an iterative procedure that we apply only to FLBF algorithm because of the computational burden associated with the full FLBF method. To tune the regularization constant in both regularization strategies, we propose the adaptive procedure based on leave one out cross-validation. In this algorithm, we run in parallel several regularized estimators equipped with different regularization gains, and at each time step, we choose the one that minimizes the local sum of squared leave one out interpolation errors. To compute these errors, we need to find the Wholly estimates of system trajectories, which are obtained by excluding the central observation from the analysis window. In the article, we have shown that these estimates don't require running additional algorithms, but can be obtained using regularized estimates that we already have. It is important to note that this adaptive scheme could also be applied to choose the most appropriate number of basis functions and length of analysis window. The proposed algorithms were tested using computer simulations. First, we generated 50 parameter trajectories by low-pass filtration of random Gaussian signals and rescaling them so that the expected variance of parameter trajectories would decrease exponentially. This reflects the power absorption loss in a real channel, because the greater the distance of the reflecting object, the greater the energy loss. An example of a frozen impulse response of a system is depicted here. As an input signal, we use a circular white binary sequence. The measurement noise was circular white Gaussian. To measure the quality of our estimates, we used the fit score averaged by time. To obtain the final results, we also averaged the fit measure over 20 independent realizations of parameter trajectories. And in all experiments, the cosinusoidal weighting sequence was used in LBF and FLBF methods. First, we compare the LBF and FLBF estimates with their regularized versions. In the second rows, we can see the effects of applying ridge regression. And in the third rows, are results yielded by a reweighted procedure. As we can see, adaptive reweighted procedure, marked by A, always improves the results of algorithms without regularization. From the figures here, presenting the results for SNR equal to 20 decibels, we can also see that the improvement is obtained for every realization. It is also worth noting that improperly designed ridge regression can deteriorate the results. According to our experiments for very small regularization gains, ridge regression can actually improve estimation results. However, we decided not to include these findings because the provided improvement is negligible. As expected, the greatest benefits from using regularization are obtained for the lowest SNR value. Next, we repeated the same experiment for iterative reweighting. As you can see from the table, the next iterations can bring further improvements, and the relative improvement is the greatest for the first 3 iterations. To summarize, the problem of identification of a non-stationary stochastic system was considered and solved using the time-localized variants of the regularized basis function approaches, both LBF and FLBF. The FLBF and LBF algorithms yield estimates of comparable quality. The accuracy of the LBF and FLBF estimators can be consistently improved by means of regularization. The reweighted LBF and FLBF algorithms provide results of a higher quality than those yielded by LBF and FLBF with ridge regression. And finally, estimates provided by the algorithm with the adaptive choice of regularization gain are of comparable quality as the best estimates yielded by algorithms incorporated in parallel scheme. Thank you for your attention.